Hello everyone, my name is Anish Anthony from Concurrent, and today I'm going to talk about hard real-time Linux for autonomous and edge AI applications. As embedded systems with Linux gain popularity for autonomous and edge AI applications, we are seeing that hard real-time is becoming a requirement for these applications. These are typically applications where the compute and data processing and control are near the source of data generation with autonomous localized actions. In this presentation, I'll show how easy it is to simulate, prototype, test, and deploy your models or algorithms on an embedded platform and have it run in real time. I'm going to use a Simulink model as an example and deploy it to run on the NVIDIA Jetson hardware. The UAV control system can fly it autonomously, or I can interface with real hardware for hardware-in-the-loop testing. The goal of my presentation is to share with you the concept of real-time simulation and testing and how easy it is to incorporate real-time into your product development cycle with commercial off-the-shelf hardware and software. We will learn about the real-time performance with and without CUDA loads using NVIDIA Jetson boards as an example, and how companies can reduce time to market by using a familiar operating system with real-time enhancements and higher level frameworks like Simulink and Simulation Workbench to simulate, test, validate, and deploy their real-time applications. I will also show how we can use tools specifically designed with real-time in mind, tools to debug, profile, tune your real-time applications for guaranteed hard real-time performance. Real-time has a lot of different meanings, and I want to make sure we are all on the same page when talking about real-time. I'm talking about the keyword determinism. Every electronics control has its own sense of a time deadline. As we move from non-real time to soft real time to hard real time, a failure to meet the deadlines become catastrophic. For some applications like internet multimedia, for example, missing the deadline means that the quality of service is not met, while for other applications like air traffic control or missile control, which are more towards the hard real-time spectrum, it may lead to mission failures. Even for soft real-time applications, we do complain if a video streaming service is not able to buffer and stream the movies consistently at an acceptable frame rate, especially during peak internet traffic hours. A typical model-based design workflow for a real-time system or a decision-making system will start with the development of the algorithm, that is, creating the algorithm or models and simulation and testing of this algorithm against the requirement. The real-time deadline for this example is 1 millisecond from input to output. The next phase is to test this algorithm on real hardware or connected with real hardware, prototyping, testing, and validating the algorithm before we deploy it. I'm going to use two examples to explain real-time application development and deployment. The picture in this example shows my vision of a customer application. The drone is powered by an embedded system and some cameras and other sensors. There are different teams working on different parts of the applications, and they test it on their hardware, and then I am responsible for putting it all together. The individual algorithms require certain amount of time to execute, as shown by the width of different colored bars. To accurately land my drone, I need to get the camera input, run my object detection and classification algorithms, and control my path to land my drone, and this has to happen within the 10 millisecond time frame. A control loop outside this time window of 10 milliseconds may result in decreased stability and reduced control as the drone flies towards the target. If for some reason I am unable to finish my calculation and control within the 10 millisecond time frame, For example, if some code from the operating system or from some other application comes and interrupts the vision code as shown by the black bar, then it is going to take longer to finish my vision algorithm, which in turn is going to push my code execution out of my 10 millisecond loop. If this happens, there is no guarantee where the drone may land at the speed it is going. The question is, how critical is it for this autonomous vehicle to meet its goal? Let me make it a little more challenging. We have some new assets in the field of vision. Now the vision system complexity has to increase, and it is going to be more compute intensive to identify and track multiple objects, and now it is very critical that we meet the goal. We will continue to develop, prototype, and test until we can guarantee in simulations that we will meet our control loop goal every time. Only then will we go for field testing and end deployment for such a critical application. Another example is this security robot. It has similar modules like the drone, and a hard real-time loop is critical to ensure the robot can move balanced in the real-world environment and under different conditions. I have seen examples where not meeting the deadline for the control loop results in the robots losing their balance or not meeting the mission criteria. Thus, anywhere we need sensor fusion and control can become a real-time system. Where it falls on the real-time spectrum depends on the application, the compute resources allocated to that application, and the acceptable worst-case execution times before it causes a system failure downstream. This picture shows how engineers tie all this together from development to deployment. Initially, they start with software models of everything and they run simulations. As they gain confidence in the real-time simulation space, they start adding hardware pieces into the loop for testing until everything is replaced with real hardware and real controllers. High-fidelity model execution on real-time hardware in the loop systems reduce the need for hardware prototypes, thus reducing the development time and cost. Autonomous systems are employing significantly more complex and rapidly evolving technologies, and X in the loop simulation and testing helps users leverage the latest that the marketplace has to offer. Now that we understand real-time systems and the applications which lean more towards the hard real-time spectrum, let us see the components that make up a real-time system. We have to make a lot of decisions. First, we have to get the right hardware or combination of hardware components for our application. Next, we make a decision on the real-time operating system. Should we go bare metal or use an RTOS? Should I use open source or proprietary? If I am using proprietary, then what will be the effort to port my application to this proprietary OS? And one of the key aspects which teams overlook is technical support. If I run into issues, can I call someone who can help me with the RTOS and help me move along? Once we decided the RTOS, we move into the development tools. Even at this stage, there are a lot of build versus buy solutions. And finally, the decision on the I/O and driver required to talk to the world by meeting hard real-time deadlines. I've worked with I/O cards where it takes more than 60 to 70 microseconds just to read all the analog channels out of the board and get it to the CPU. So if I have a real-time loop of 100 microseconds, then such a card is not a good option because I will only have 30 microseconds remaining for my compute algorithms. For X in the loop testing, my hardware of choice is the NVIDIA Jetson AGX dev kit because of the available PCIe slot, where I put in an FPGA card for running models and I/O requiring timing in the nanosecond range. The FPGA card gives me a super ability to mimic a ton of signals flowing in and out of my control system so I can talk to the outside world. In the demo today, I'm going to use a ConnectX Sentry X NVIDIA Jetson system. We could also choose from a variety of COTS hardware from small embedded systems to large systems with up to 224 CPU cores and terabytes of RAM and hard disk space. Now that we have chosen the hardware, let's move to the real-time operating system. Our choice here is Red Hawk Linux, which provides low latencies and determinism required for real-time systems. It has good support for different hardware platforms and is optimized for CUDA I/O. Red Hawk fully leverages the power of multi-core and multiprocessor technology, making it ideally suited for challenging real-time applications. Red Hawk Linux is compatible with the most popular Linux distributions out there, and this compatibility helps when anyone has a need for any real-time capabilities, and for them it will be easy to transition to Red Hawk Linux. It even supports the PRT kernel if desired, so that you can test and compare with Red Hawk's real-time features. Red Hawk Linux has over 300 to 400 add-ons to the standard Linux kernel to provide real-time capabilities, and CPU shielding is one of the most important features. In this example, I'm showing a 2-socket system with 12 cores each, but the same concept applies to the NVIDIA Jetson. The Jetson Xavier will have 8 cores, which we can see during the end of the presentation how I'm tuning the system with 8 cores. As the name suggests, in CPU shielding for a multi-core system, we shield the CPU and memory from interrupts, local timers, and processes interrupting your algorithm or code which you wish to run in real time. This means that your application or processes running on a shielded CPU core will get the full CPU bandwidth, and if that application is waiting to process an interrupt, for example from a camera system, it will be able to respond as soon as it gets the interrupt. This results in the lowest response latency and high determinism. For engineers who are interested in bringing real-time to ROS or robotic operating systems, shielded CPU cores can guarantee its real-time performance. In this example, I'm running my ROS threads on 4 shielded CPU cores with real-time scheduling policy of Sketch FIFO and a priority of 60. I'm not going to go into the technical details here, but you get the idea. We only allow interrupts that ROS requires to pass on the ROS threads, thus providing lowest latency and improving determinism. Now that we understand shielding, let us look at some Red Hawk Linux benchmark results. These are open source tests to benchmark, and the links are in the slide for anyone to try on their system. PDL or process dispatch latency is a measure of how fast your process can respond to interrupts. As you see, the average PDL with and without CUDA loads on the system are around 15 microseconds across the family under Red Hawk Linux. Without Red Hawk Linux, the PDL times are in the milliseconds. For some applications, the millisecond latency may be acceptable, but for others, they need a deterministic response time in the microseconds range, and Red Hawk Linux can provide that. With the Red Hawk Linux operating system, we can run our code in real time. However, we can significantly reduce our time to market by using higher level modeling and simulation tools like Simulink and Simulation Workbench without having to worry about writing C code or real-time drivers or connecting to signal conditioning and I/O. Simulation Workbench real-time database is what makes this easy, and SimWorkbench makes it easy to interact with model signals and parameters via program and operator interfaces in real time. In this example, I'm going to show a Simulink model of an UAV, generate C code, and transfer the code over to the ConnectX SentryX, where I have a joystick connected to it, and run this model in real time. I have also written some C code for autonomous or autopilot operation, but I'm going to override it with my joystick controls. First thing we do is connect to the target system from MATLAB Simulink. MATLAB Simulink can run on Windows or Linux. Next, we create a real-time database from the Simulink model. This real-time database or RTDB will make the model I/O independent. The RTDB is nothing but an ASCII file of mappings, and internally it is a C shared memory structure, which makes it easy for any other code to talk to this model. After the RTDB is created and uploaded, all I do is generate, export, and make, and create the model binary on the Linux system. Once Simulink is done, we are going to go into Simulation Workbench and look at the real-time database. This is the Sim Workbench Control Center, and I'm going to look at the RTDB and see if all my points are available from the Simulink model. Next, I'm going to map the model variables to different I/O. I'm going to map to the joystick I/O and also to the SIGI interface. SIGI is a protocol that helps me talk to the image and visual system where we are running Diamond Visionics partner software. I could easily map it to another I/O board if I desire. Next, I'm going to set the model to run on CPU 3 with the RTDB CCUR_aircrafts. I also have C code which is running as a test script which has some autopilot code. I can also add another model to this test and run it in parallel. Now I'm going to run the test to execute the model in real time. As you see, the model has started executing, and we go to the real-time viewer and see the parameters changing in real time. I'm going to add some of these variables to my table and see the values changing. I can also see the data on the chart in real time. Remember, we have a SIGI interface, and on the image and screen, we can see the UAV flying over Hawaii, and I am controlling it with the joystick. While the model is running, we can see how much time the model is taking, where it is running, and I can change the CPU where it is running in real time. I can change SIGI out to move from CPU 3 to CPU 5. And I can also shield the CPU cores, helping to improve the determinism of the system. In Simulation Workbench, we can also easily create HMIs and real-time plots to show data trends. In this example, I have the Simulink model and a C code autopilot_test running in real time. If I needed to debug my code to understand what is going on with my code, I'm going to use Night View, which is a hot patch debugger, which has minimum impact on the real-time performance of the system. In this example, I know the function call that I need to break to, so I'm going to set it up and set the breakpoint. So when my model runs, I can come and stop it, and like any other debugger, I can step through my code and look at my variables and try to understand what my code is doing. If for some reason you don't have the C source code available, the debugger will default to assembly view, and this will help you understand at the lowest level what your code is doing and what your program is doing, and help you debug and fix any problems. To understand how your code interacts with other applications and kernel programs running on the system, we are going to run a real-time trace on the system. The night trace tool shown here captures everything what is going on the system across all CPUs. It captures all the kernel events and the application events. If we zoom into the nanosecond range, we can dig down even further as to what the system is doing. On CPU 3, we can see that we are running CCUR_aircraft model, and on CPU 6, we are running our autopilot_test.c code. And we can even measure its execution time of 1 microsecond. We can also see that the two executions are spaced around 1 millisecond apart, which was the frame rate chosen for our simulation. We can dig down even further into our code and see that there are many semop operations we are doing inside the code. We can also see that CPU 3 is sharing the CPU with another task, the SIGI async task. This is a very powerful tool, and kernel and user level application tracing is very useful when you are trying to understand at the nanosecond or microsecond level what the system is doing with your code. Now that we understand how our application behaves in the system, we can tune the system to improve the real-time performance. With NightTune, we can analyze and adjust system activities with ease. We can monitor the status of a CPU, including information about shielding and process and interrupt bindings. We can see with NightTune where a code is running, on which CPU. We can even see the threads, and we can move the CPU affinity around. We can also shield CPUs and have our applications or processes run on this shielded CPU to help guarantee response times. We can also look at the memory consumption. Once we save the tuning, we can always restart the system with the tune parameters to guarantee the same hard real-time performance every reboot. To summarize, I've shown how you can run your algorithms in real time using the familiar Linux operating system with Red Hawk's real-time enhancements. The tools, real-time focused products, and support can significantly reduce your time to market with real-time applications. Concurrent Real-Time provides a complete ecosystem with long-term support for programs with lifespans of 20 plus years. We also create custom solutions for our aerospace and defense customers, from custom I/O boards to FPGA-based solutions. Hopefully, this workflow resonates with you, and if you have any questions, please connect with me and I will be glad to assist.